Okay, so in this video, we are going to look at photoelectron spectroscopy. Now, we'll also have a poll goal that goes into some detail on this, but it's not something the book that I'm having you reading talks about too much or like a huge amount. And so I want to talk about understanding how to read these and the kind of problems that you can see. Okay, so first of all, if you're looking on this graph, you can notice that further to the left, we have bigger numbers, and the x-axis represents the binding energy. The units are megajoules per mole, or EV. The units are not super important for a lot of these problems, at least for the unit 1 problems that we have. But basically, the bigger numbers are on the left. So that means that the more the electrons with a stronger attraction to the nucleus are further to the left on the graph. And then the y-axis is representing relative number of electrons. One kind of line on the y-axis for the AP questions usually doesn't represent necessarily one electron, but it represents relative number. And so based on the height of different peaks, you can compare them. So the height tells, again, the relative number of electrons. And the further to the left, that means higher bonding energy. Well, how does something have a higher bonding energy? All the electrons have the same charge. We're dealing with the same nucleus. And so the difference is how close they are on average. And so if you recall learning about electron configurations, like 1s is on average closest to the nucleus. That's why it gets filled first, because that's the lowest energy position available, right? And lower energy is favorable, just like gravity, something falls off a table, right? So closer to the nucleus is going to be favored, whereas the further, like higher energy electrons with a lower bonding energy are going to be filled in later, right? If like kind of stacking things on top of each other off the ground. Okay, so this first one is just hydrogen, and so this is 1s1. And so you can see there's just one electron. It shows the bonding energy. Then we look at helium. Notice going from hydrogen to helium, the binding energy is a little more, and the peak is twice as high. So this is because there's 2 electrons here, and this is 1s2. Why does the peak move leftwards? Because there's more protons, right, relative to that energy level, and so a higher amount of attraction. And then we go to lithium. So you can see this would be 1s2, and here we have 2s1. So the 1s electrons are closer to the nucleus, and there's 2 of them, so the peak is twice as tall, and they have a higher bonding energy than the 2s1. Then we look at beryllium. We have 1s2, 2s2. Peaks are same height, but the 1s2 is going to be have a higher bonding energy. And notice again, the bonding energy the binding energy is higher than lithium by a little bit because there's more protons in the same amount of energy levels, and so higher attraction by a little bit of the electrons to the nucleus, a higher effective nuclear charge. So then we look at boron. Here we have 1s2, 2s2. Now those peaks are the same height, right? And now after 2s2 comes 2p1, right, with boron. And so we have, right, if we're looking at I should have my periodic table out when I'm doing this, because of course you get your periodic table on the exam, and if you walk through the periodic table, it's really easy to see what's going on, right? Because boron has 1 electron in 2p. Okay, then we go to the next one. So we're going to have, for carbon, 1s2, 2s2, 2p2. Again, notice the 2p2 same height as the other ones now, same number of electrons, but 2p2 is a lower bonding energy than the others, right? Because those electrons on average are further from the nucleus. And then we have nitrogen. Again, notice as I'm going across the period, the peaks are shifting slowly leftwards. That's because of a higher effective nuclear charge, because of more protons in the nucleus while being in the same energy level. This is 1s2 peak, we have 2s2, and now 2p3. So notice this one is higher than the other ones, right? There's more electrons in it. It's not double the height because there's not double the electrons, but it's 1.5 times as big. Then we go to oxygen, 1s2, 2s2, 2p4. Now notice the peak is twice as high because there's double the amount of electrons in it, and it's the furthest right because it has the least bonding energy. But again, notice as I'm going right across the period, there's a higher effective nuclear charge due to more protons. Okay? Then I have 1s2, 2s2, 2p5 with fluorine, right? That peak's getting bigger as there's more electrons. Now, with neon, 1s2, 2s2, 2p6. Hopefully you see, you don't have to memorize what the peaks look like for every element. If you just reason through, okay, for this left, that has to be 1s2, right? Then after that comes 2s2, if you remember electron configurations, which hopefully is not a problem for you. It's something I have videos on, but hopefully you also learn that in your general chem. And then we have 2p6, right, which is going to be higher than the others, and that's next in line. And then we go to the next element. And hopefully, right, even if I blocked out what this element is, right, I say, okay, tell me what it is. I don't know. You tell me, what could this element possibly be? Well, you'd say, okay, first we have 1s2, then we have 2s2, then we have 2p6. Notice it's a lot higher because there's 6 electrons as opposed to 2. And then what comes after 2p6? 3s1. What does this have to be? Sodium! There we go. Let's look at the next one. Notice again the peaks are moving slightly leftwards. So magnesium, the peaks have shifted left as compared to sodium because of a higher effective nuclear charge, right? Because of more protons relative to the energy level. So we have 1s2, 2s2, 2p6, and now this is 2 electrons, so that final peak is higher, 3s2. And then we go to aluminum, 1s2, 2s2, 2p6, 3s2, and now 3p1. Okay? So, let's say you have a problem like this, and they are asking you, okay, what elements, so they could first ask you, what elements are these? Okay? So you could get a question like, what elements are these, right? And then you'd reason it out. You'd say, okay, this has to be 1s2, this has to be 2s2, this must be 2p6, this has to be 3s2, and now this has to be 3p3, right? Because it's, even if they didn't give you number of electrons and you're just looking at relative size, you can see that it's 1.5 times as tall as 3s2, so that means there's 3 electrons, right? Not 2, not 4. And so because of that, then we can look and say, okay, what's 3p3? Well, that's going to be phosphorus, okay? And then we could look at this one and say, okay, 1s2, 2s2, 2p6, 3s2, 3p. Let's see, now it's twice as tall. This is 3p4. And then you could look at your periodic table and be like, what is 3p4? Well, let's see, 1, 2, 3, 4. That's one more than phosphorus. That's sulfur, okay? And then they could have another question like this. They could be like, will or let's say like this, why are the peaks on sulfur higher bonding energy? Or they could say shifted to the left. Or they could ask you to predict, will the peaks be in the same place or where will they be? Or they could be like, What would 3p4 look like? Draw the 3p4 peak for sulfur, something like that. And you'd have to draw it the right height, and then also recognize that compared to this peak here, this peak, if they were asking you that question, should have shifted very slightly to the left. What is the reason for that? Again, here on this one, they probably wouldn't ask you that one because it doesn't look like there's that much of a difference, right? But in general, well, maybe they could, and you would just predict the general trend. In general, the rule would be, right, that if there's more protons relative to the energy level, there's a higher effective nuclear charge, and therefore the peak shift to the left with a higher bonding energy. Now, if we're looking at sulfur and oxygen, those might be exceptions to the rule, and you don't have to have exceptions memorized, but you do, as I talk about in other content, just need to be able to explain just certain exceptions and why they take place. But that's not the focus of this video. And I haven't seen a Unit 1 question that deals with that too much. Or, well, no, there is one on oxygen that I think you'll see, but that's something we talk about in another video. Okay, and so you could have another one like this where, pause it, see if you can identify what they are, but hopefully you get the rundown. You just do your electron configurations. 1s2, 2s2, 2p6, 3s2, 3p6. Oh, this must be 4s1. And then I look on my periodic table and I say, gee whiz, what is 4s1? That's potassium. And then I look at the second one and say, okay, 1s2, 2s2, 2p6, 3s2, 3p6. But this last peak has one more, right? 2 electrons in it. That must be 4s2. So that's got to be calcium. And then again, they could ask you, why do the peaks on calcium shift left compared to potassium? And you say the same energy level. Calcium is one more proton, higher effective nuclear charge, therefore greater Coulombic attraction, right? And so higher bonding energy, something like that. And those are the kind of problems you will see for this particular topic 1.6 over and over and over again. So work through the practice problems when I give them to you, and remember your electron configurations.